Hey everybody. What are we at here? There's the usual attendance and tutoring and link to the spring quarter evaluation, not the fall quarter evaluation. So you guys have a quiz this Friday, and talking about lots of stuff. Do you guys have any? I feel like someone asked me something specifically they wanted to see. Maybe I'm thinking of a different class. I think I am thinking of a different class. We can talk about graphing. We can talk about L'Hopital. We can talk about optimization. Where do you guys want to start? Actually, I want to do a graphing example before we do anything else. So I'm going to do a graphing example. If there are other things you want to see, just let me know. But we'll start with some graphing. Yeah. And here's the attendance and stuff again. So let's start off with this example I've got. Ooh, come on. And so the reason we've been doing all this first derivative and second derivative test stuff is so that we can make a graph that is more complete. Let me fix this here. Sorry, my face up close. All right. So I want to graph this function. F of x equal to 2x cubed minus 12x squared plus 18x minus 108. And I want to find all of the things, meaning I want to find the intercepts. I want to find where the function has a relative max and a relative min, meaning I also want to find where it's increasing and decreasing. I also want to find any inflection points and the intervals where it's concave up and concave down. So basically all of the first derivative and second derivative features. First things first, so we need to find the intercepts. The y-intercept is pretty straightforward. We just set x equal to 0. Set x equal to 0, f of 0 is going to be negative 108. I did pick these numbers specifically so that it turns out kind of not terrible. You'll see that. The x-intercepts can be challenging, especially if the degree of the polynomial is anything higher than the second degree. This is the third degree. This one does happen to factor in a kind of nice way. It factors by grouping. So if you take the first two terms, I can factor out a 2x squared. So from here, I'm getting a 2x squared. Sorry, from these first two terms. I'm left with x minus 6. And from these two terms, I can factor out 18. 18 is a factor of 108. It's actually, I feel like it was 0. Now I'm really thinking I'm not wrong. I might have to change the sign, but we'll go with it for now. I'm going to factor in 18 here, and we're left with x minus 6. Oh, I could have factored out a 2 from the very beginning. That might have been smart. In either case, this factors as x minus 6 times 2x squared plus 18. Or x minus 6 times 2 times x squared plus 9. So if I set that equal to 0, I only get one x-intercept. I get x equal to 6. And setting x squared plus 9 equal to 0 won't give me any intercepts because there's no real solutions there. So that's all the original function stuff, right? Y-intercept, x-intercept. Now I'm going to find what I usually call the first derivative stuff. I'm going to find where the function is increasing or decreasing. I'm going to find any relative extrema. So I'm going to set f prime of x equal to 0. And so in doing that, I'm going to say, well, my derivative is going to be 6x squared minus 24x plus 18. And set that equal to 0. And yeah, I do think I missed a sign. Sorry, guys. So I made a small error when I was writing this problem. Let me fix it right now because I can definitely see. Yeah, 6. No, that's right. I'm just a little crazy. Sorry, that's fine. So I'm going to solve this. I'm going to factor out a 6. Left with x squared minus 4x plus 3 equals 0. And then factoring this, I have x minus 1 times x minus 3 equals 0. So my critical values are x equal to 1 and x equal to 3. Now I'm going to make a sign chart. I have time to open another new pen. I'm trying not to go through these pens too fast. Make a sign chart for the first derivative. I'm going to put the critical values on my sign chart. And then I'm going to look at what the sign of the first derivative is in each of those 3 intervals. There's the attendance again, by the way. So I pick a number larger than 3 and I plug it into the first derivative. Well, here's the thing. I don't want to plug it in here or here. I want to plug it into the most factored form. So I pick a number like 4 and plug it in. I get 6 times a positive number times a positive number. 4 minus 1 is positive, and 4 minus 3 is positive. So the whole thing is positive. Pick a number between 1 and 3 like 2. 6 times positive times a negative, the whole thing is negative. Pick a number like 0. 6 times a negative times a negative is positive. So the function is increasing, decreasing, increasing. And I usually don't write it down because I think the chart makes it obvious, but you might need to state this increasing on the interval from negative infinity to 1, union 3 to infinity. And it's decreasing on the interval from 1 to 3. And we can see that with that little arrows, right? It's going up, and then it's going down, and then it's going up. And so that also lets us state, and I'm going to write this on this side of the board. So at x equal to 1, do we have a relative maximum or a relative minimum? What do we have right here if it's going up and then going down?
A max.
Exactly. We have a relative maximum. So we have a relative maximum. Really, we should probably actually find the y value. So what I should have actually said is at 1 comma f of 1. We have a relative maximum. And then we'd actually have to find f of 1. We should probably do that. Let's see. F of 1 is, well, plugging in 1 is easy. It's going to be 2. Well, in fact, I should be smart. I should plug it into the factored form. And plugging into the factored form is usually easier. If I plug in 1 here, I get 2 times negative 5 times 1 plus 9 is 10. So I get negative 10 times 10, which is 100. Sorry, negative 100. So it's at 1 negative 100. That's where we have a relative maximum. And then the relative minimum is going to be, well, so I should say, what do we have at 3? Oh, we have a relative minimum at 3 because the function is going down and then going up. So we have a relative minimum at 3 comma f of 3. F of 3, again, plugging in 3 here is especially kind of not great, right? It's 2 times 27 minus 12 times 9. Here it's a little easier. Plugging in 3, I get 2 times 3 minus 6 is negative 3. And 3 squared is 9, and plus 9 is 18. And 2 times negative 3 is negative 6, and negative 6 times 18 is negative 108. And here's something that I think is worth knowing. Once you know all the first derivative stuff, you can mostly draw a pretty good graph. So I'm going to actually start drawing my graph right now, even though I haven't done the second derivative stuff yet. And it's going to be not quite to scale because my numbers are kind of big. So let's see. I've got a y-intercept at negative 108. Let's say that's like down here. Let's say that's negative 108. I've got x-intercepts at, well, just one x-intercept at 6. So let's say, let's give ourselves a little bit of room. Let's say that's 6. And I have a relative maximum at 1 comma negative 100 and a relative minimum at 3 comma negative 108. So I'm going to double check my negative 100. 1, that's only right, okay. So 1 comma negative 100. I feel worried about this. Oh no, I guess, let's see. and a relative minimum at 3, -108. Maybe what's a little bit more room. Okay, this is gonna work out fine. It just felt like it was gonna be weird. Let's say that's 1, 2, 3, 4, 5, 6. So there's 1, -100, and that's a relative maximum. And 1, 2, 3, -108. There's my relative minimum. So I'm also going to use this sign chart. I can see this increasing before I get to 1, then decreasing between 1 and 3, then increasing after 3. So it's going to be increasing until I get to 1. So it's going to look like this. And then after I get to 1, it's going to be decreasing until I get to 3. After I get to 3, it's going to be increasing. And it's going to have the x-intercept of 6. So I can draw, oh, go ahead. I thought I heard someone. I can draw almost the whole thing without really knowing the second derivative. The only thing the second derivative is going to tell me is exactly where it's concave up and concave down and where the inflection point is. I can see it's probably concave down from -infinity to some point between 1 and 3. It's probably going to be 2. And it's concave up everywhere after that. So let's take a look. So finding the second derivative, I should probably have the first derivative again. The first derivative was, let's write the unfactored form, 6x squared minus 24x plus 18. And the second derivative, the derivative of the first derivative is 12x minus 24. We set that equal to 0, we can factor out of 12, and we get x equal to 2. So looking at the sign chart for the second derivative, we pick our one critical point, or critical value, and we look, if x is bigger than 2, then the second derivative, I put it like 3, 12 times 3 minus 2 is positive, so it's concave up. If I find something less than 2, like 1, 12 times 1 minus 2 is negative, so it's concave down. And if the concavity is changing at 2, we would say that we have an inflection point at 2, f of 2. I suppose we should plug in 2 to figure out what f of 2 is. Then plug in 2, you get 2 times 2 minus 6 is -4 times 4 plus 9 is 13. So 2 times -4 times 13. Which is going to be -104. And we should also say it's concave up on the interval from -infinity, sorry, on the interval from 2 to infinity. And it's concave down on the interval from -infinity to 2. Questions about anything here before we do another example? Okay. Let's see. I feel like there's something else I wanted to say. So remind me, for Sanders class, you guys don't have a final exam. It's like a final quiz, right? Does that sound right? Yeah, final is a quiz. At least that's what I have here in my notes. Okay. I mean, this is something you don't have to prepare for it, but just something to think about. Okay. All right. Let's look at this. Let's graph the following. Let's graph f of x equal to x to the 4th plus 4x cubed. And again, when someone says graph a function, at least in calculus, what they really mean is find all the things. Find all the first derivative things, find all the second derivative things, find the intercepts. So I always kind of start with the intercepts. So intercepts. So y-intercept, set x equal to 0. I'm going to get y equal to 0 plus 0 is 0. For the x-intercept, I already know why I know the origin is going to be one of them because I got the origin as a y-intercept, so it's also an x-intercept. The x-intercept, I'm going to set the function equal to 0, or y equal to 0, whatever you want to call it. So we get x to the 4th plus 4x cubed equal to 0. I'm going to factor. I'm always factoring. I'm trying to solve this. I'm going to get x equal to 0. And I'm also going to get x equal to -4. So those are going to be my two intercepts on my graph, my x-intercepts. Okay. Those are the first. I should say the other things you also do look for when you're graphing something is horizontal and vertical asymptotes. Since this function is polynomial, we don't have any horizontal and vertical asymptotes. So that's something you also look for before you start looking at the first derivative and second derivative stuff. So now we're looking at the first derivative. F prime of x is 4x cubed plus 12x squared. And we're going to factor because we're trying to set it equal to 0 and find the critical values. So setting it equal to 0, I need to factor out a 4x squared. I'm left with an x plus 3. Squared so I get x equal to 0 and I get x equal to -3. Let's go ahead and look at what's happening on the sign chart here. Oh, sorry, 0. I should have drawn. Could have zoomed -3, 0. So point of interest here, you only want to include 0 if it's actually one of your critical values, right? We don't really need all the points. We only need the ones that are critical values from the first derivative. So looking at the sign chart, if I plug in something larger than 0, like 5, plugging it in here to f prime of x, 4 times 5 squared is positive, 5 plus 3 is positive, 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 positive. I don't actually care what the number is, I just care what the sign is. Picking something between 0 and -3, like -1, 4 times -1 squared is positive, and -1 plus 3 is also positive, and the product is positive. And then plugging this in at -4, 4 times -4 squared is still positive. The -4 plus 3 is negative, and the positive is negative. So we see that the function is decreasing, then increasing, then increasing. So, do we have a relative maximum anywhere? Do we have a relative maximum of 0?
No.
How about -3?
That's a minimum.
Correct. So we definitely have a relative minimum at x equal to -3, and then we should find the y value, f of -3, plugging that back into the original function again. I would much rather plug it into the factored form instead. I don't want to do -3 to the 4th plus 4 times -3 cubed. That sounds like a pain. So I'm going to plug it in. What's that? Sorry, I keep thinking I'm hearing stuff because like people are working outside. So if you're saying something, definitely speak up. But sorry I keep being like, hello. Plugging in here is nicer, right? It's easier to do -3 cubed times -3 plus 4. That's going to be -27 times 1. That's less terrible to calculate, in my opinion. There was something else I wanted to say here. No, I think I'm just thinking ahead to the next problem. Okay. Oh, I know what it is. So this is yeah. So I would say the function is decreasing on the interval from -infinity to -3. And what about increasing? This is kind of a, go ahead.
-3 to 0, and then the union 0 to infinity.
So normally that would be correct. And so here's the issue. The issue is that if it's increasing, a lot of the times it's undefined at the point where where the derivative is, where you have a critical value. In this case, it's not though. Right? This function is totally defined at 0. So if it's increasing, and the function is defined at the point between those 2 points, you have to include it. And so we actually say it's increasing from -3 all the way to infinity. And this will be more clear, I think, once we graph it. And then we'll do another example where we have kind of the opposite thing happening. Yeah, in this case, it's actually increasing on the entire interval from -3 to infinity. Let's do the second derivative stuff, and then we'll graph it. Okay. Sorry, my first derivative was 4x cubed plus 12x squared. My second derivative is going to be 12x squared plus 24x. Set that equal to 0, factor out of 12x, left with an x plus 2. So we're getting x equal to 0 and x equal to -2. Number line, put the 0 and the -2 in the right order, like the order is important. Integer larger than 0, like 1, and plug it in, it's a positive times a positive. Integer between 0 and -2, like -1, it's a negative times a positive. It's negative. Integer like -3, it's a negative times a negative. So it's concave up, concave down, concave up. So I would say it's concave up on the interval from -infinity to -2, union 0 to infinity. It's concave down from -2 to 0. And here we do have an inflection point at both -2 and 0, because you have an inflection point whenever the concavity changes. It doesn't matter if it's positive to negative or negative to positive. If the concavity is changing, you have an inflection point. So I'd say we have inflection points at 0, 0, right? Because we know if you plug in 0, you get 0 out. We already did that. And we also have one at -2, comma, f of -2. So let's back to my original function for just a second. We'll plug in -2 here, right? Because that's the easier way to do it. -2 cubed is -8. -2 plus 4 is 2. -8 times 2 is -16. Then we can graph the thing. I'm just kind of putting everything on this. I got the point 0, 0. Let's see. 1. Sorry, negative. Go negative. -1, -2, -3, -4. My intercept at -4, right? -4? Yes, -4. And then I have a relative minimum at -3, -27. So that's like down here. And it's going to be, when I'm graphing this, I'm mostly looking at the first derivative information. I can see it's going to be decreasing until I get to -3, increasing, and then it's going to kind of flatten out at 0, right? Because since 0 is a critical point, the derivative was 0. So it's going to be like increasing, and then it's going to kind of like flatten out, and it's going to keep increasing after that. Kind of like a cubic function does. And then it's going to be increasing after. So I can see that it's going to be, so before I get to here, it's going to be decreasing at this point and this point. Decreasing, and then when I get, I'm not going to turn around, so I have to start like kind of turning around, increasing. And now when I get to this point here, it's going to flatten out because the derivative is 0, but then it's going to keep increasing after. And then at 2, -16, which I'm just going to kind of draw in there, right? Or -2, -16, right? There's my inflection point, where it changes from being concave up to concave down to concave up. Right, so just so you guys can see that, right? This section here is concave up. This little section here between -2 and 0, which again doesn't look perfect, but oh well. And this is concave down, and this section here this is concave up because it's opening upwards, and here it's kind of opening downwards. Questions? Before actually, so I just want to point out, from -3 onward, the function is increasing, even at 0. Because to be increasing, it just means if you move to the right, the function gets bigger. So from right, we're getting closer and closer to 0, and anywhere, left of 0, right of 0, at 0, if you move from left to right, the function is getting larger. So we say the function is increasing on the entire interval from -3 to infinity. Other questions? It's not really the example I want, just one sec here. I wanted like a specific graphing function I was looking for. Oh well. Okay, let me do one more graphing problem and then we can move along to other things you guys have questions about. Or we can do graphing all day. Also, here's the attendance again, in case you guys want. Please do fill it out, as well as the spring quarter evaluation. I would appreciate you doing both of those things if you have not already. I appreciate it if you have them as well. Okay, now I was going to come up with a graph that was going to be not terrible. Sure. Okay. Yeah, let's do that. Let's say f of x is yeah, let's do that. X plus 2 squared over x squared minus 1. Okay, so here's a function. It's gonna be a little bit of work to find all the things, but let's start off. So first things first, y-intercept, and set x equal to 0. F of 0 is going to be, let's see, if I'm putting 0 on top, 0 plus 2 squared is 4, over 0 minus 1 is -1, so I get -4. X-intercepts. So when you're setting a rational, when you're finding the x-intercepts for a rational function, you're setting the whole thing equal to 0, but it really just ends up being setting the top equal to 0. All right, I set x plus 2 squared over x squared minus 1 equal to 0. The first thing I'm going to do is I'm going to multiply both sides by the denominator. The left side is just going to be x plus 2 squared. The right side, well, 0 times anything is 0. So it really just ends up being the same as setting the top equal to 0. And then the only solution here is x equal to -2. So those are my intercepts. We also have to think about asymptotes here. So vertical asymptotes we find by setting the denominator equal to 0. We need to find where the function is undefined. That is assuming, of course, that we factored and canceled everything we can. We have, well, there's nothing more to factor and cancel. We could factor the bottom as x minus 1 times x plus 1, but nothing to cancel out. So if we set the denominator equal to 0, we factor, and we get x equal to 1 and x equal to -1. So we have vertical asymptotes at 1 and -1. And then horizontal asymptote, we can find by comparing the degree on top and the degree on the bottom. If I multiply at the top, sometimes it's actually good to multiply it out. So we multiply at the top, it's x squared plus 4x plus 4. The bottom is still x squared minus 1. So can anyone tell me what the horizontal asymptote is for this function? It's a pretty important.
1?
Yeah, it's definitely 1. And the reason it's 1 in this case is because the degree on top and the degree on the bottom are both the same, right? They're both degree 2. When the degrees are the same, it's the quotient or fraction of the leading coefficients. The leading coefficient on top is 1. The leading coefficient on the bottom is 1, so it's 1 over 1 is 1. If the degree on top were lesser, then the horizontal asymptote would be 0. So if you were graphing something like g of x equal to x plus 2 over x squared plus 2x plus 1, this one would have a horizontal asymptote of 0 because the degree on top is strictly less than the degree on the bottom. Maybe we'll do that one next. So the horizontal asymptote here is y equal to 1. Yeah, that's all. There are, sometimes you can tell what the horizontal asymptote is after you see the graphing, but when it's rational like this, you can usually just tell. There are other functions like exponential ones that sometimes have a horizontal asymptote where you have to use L'Hopital's rule to find it. So We can talk about that too if you guys want. Let's see here. So then the first derivative stuff. So the first derivative. So I'm going to do the bottom. The bottom is x squared minus 1, not 2x, times the derivative of the top. The derivative of x plus 2 squared is 2 times x plus 2 to the first, times the derivative of x plus 2, which is just 1, minus the top, the bottom derivative of top minus top x plus 2 squared times the derivative of the bottom, which is just 2x, all over the denominator squared. Okay, and so when you're doing this, you have to factor the top as much as possible because we're trying to figure out where this is equal to 0. And the only way we can really get that is if we factor the top. So we'll factor the whole thing really. So I can factor out, I see a factor of, I've got x plus 2 to the first here, I've got x plus 2 squared here. So I can factor out one of those. We can also factor out a 2 from each of these. But that's about it. So I can factor out a 2 times x plus 2. And I'm left with, well, here I'm left with an x squared minus 1. And here I'm left with, well, there's still an x plus 2. And there's also an x. All over x squared minus 1 squared. And then I should left myself a little more room. Simplifying inside here, well, first of all, I'm going to distribute the x. I'm going to get x squared plus 2x. Sorry, I'm being a little here. It's minus x squared plus 2x. So simplifying the top, you get 2 times x plus 2 times the x squared minus x squared cancels, and you get a negative 1 minus 2x, or negative 2x minus 1. This is a little bit complicated. So if I look at this, I can get critical values, critical points, I should say, not critical values, when x is equal to negative 2. When x is equal to, I feel like I need to double check my work here just to be absolutely sure that I didn't make some dumb mistake. I factored out 2 times x plus 2, I had an x squared minus 1. Factored out x plus 2 times 2, and I had x times x plus 2. Now, I was just worried I'm doing something dumb. Okay, that looks fine though. So I get a negative 2, that makes the numerator. I also get a negative 1/2. If x is negative 1/2, and negative 2 times negative 1/2 is positive 1, minus 1 is 0. I also get plus or minus 1. Now, here's the thing I was saying last week. We know that plus and minus 1 aren't actually critical values because they're not in the domain of the original function. If you plug in 1 or negative 1 to the original function, that's where we have a vertical asymptote. They're still important to include on the sign chart for the first derivative because they're going to tell us that the function changes from being increasing to decreasing. And it's going to help us see the shape of the function if we're graphing it. So here's my sign chart. I've got negative 2, negative 1, negative 1/2. That's a lot of numbers all really close to each other. And positive 1. So I'm going to start with taking something larger than 1, and then I'm going to talk about actually a different way of doing this. So I got a larger than 1, like 5. Plug it in. 5 plus 2 is positive. Negative 2 times 5 minus 1 is negative. 5 squared minus, well, this thing squared is always positive on top. Sorry, I said positive, negative, positive, so it should be negative over there. And, well, so here's the thing. You can keep plugging in points. It gets a little bit tedious though, especially when you have like kind of short intervals here. I can tell you a big 0 here, that'd be fine. But you could also say that, well, so the problem with this one is kind of funky. The thing is that what I really need is actually the factor the bottom if I want to do this. So I want to factor the bottom. X squared minus 1 squared is x minus 1 times x plus 1 quantity squared. And then I square each thing and I get x minus 1 squared times x plus 1 squared. There's a reason for this. And I'm showing you this. When a factor comes from an odd powered piece, sorry, when a 0 comes from an odd powered factor, the sign's going to change. When a 0 comes from an even powered factor, the sign's going to stay the same. So 1 comes from this even powered factor, right, because you plug in 1, it makes this part 0. And when it's even, the sign's going to change. I mean, oh my God, the sign's going to stay the same. And the way we know that is because, well, we can plug in 0. Right? If I plug in 0, this is positive. So this is still positive, just like it was when I plugged in 5. This is still negative. This part, the inside changed from being positive to negative. Since it's squared, even power, it's not going to change the sign overall. Right? Whether the insides are negative or positive, squaring it's going to always make it positive. So it's still positive, negative, positive, positive. So it's negative overall. And then the negative 1/2 came from this factor, which is raised to an odd power of 1. When the power is odd, the sign is going to change from negative to positive. Now we could try plugging in a value, but it's kind of a pain, right? Something between -1 and -1/2 is like -3/4. -3/4 plus 2 is positive. This one's going to be positive, this one's going to be positive because they're both squared. And -3/4 here, let's see, -2 times -3/4 is positive 3/2 or 1.5. And positive 1.5 minus 1 is positive. So it's positive, 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 positive. And then when we go from this side of -1 to the next side of -1, it's going to stay the same because -1 came from this factor, which is an even power. You could also pick a number like -1.5, plug it in. This part's still positive. This part's still positive because right, -2 times -1.5 is positive 3 minus 1 is positive. This is positive, this is positive because they're both squared. And finally, going over here to the other side of -2, it should change signs because -2 came from this factor, x plus 2, which is raised to an odd power of 1. Because of the -3, it's going to be negative, positive, positive, positive. Okay, so it's kind of a mess, but it's decreasing, increasing, increasing, decreasing, decreasing. And so if I was going to talk about the intervals where it was increasing or decreasing, and so this is where things are going to be different than last. So this is where your intuition from last time is correct. I would say that it's increasing on the interval from -2 to -1, union -1 to -1/2. The reason we don't include the -1 here is because the function is undefined in -1. In a similar way, we would say it's decreasing on the interval -∞ to -2, union -1/2 to 1, union 1 to infinity. And we don't include the 1 because, just like in the previous one, the function is undefined at 1. Okay, that's a lot of work. So here's what this is going to look like. And I might skip the second derivative because the second derivative is probably going to be really messy. Sometimes people get lazy and skip the second derivative. We can do it if you guys want, but I'm telling you right now, it's going to be gross. So here's how this is looking. Oh, sorry. Well, let's. So actually, okay. Let me recreate my sign chart over here. Negative, positive, negative. We also know that at -2, we have a relative what at x equal to -2. If it's decreasing, increasing. What do we have at -2, guys? A relative maximum or a relative minimum?
Minimum.
Yeah. And then we should find the y value. Y equals f of -2, which is going to be 0. We already knew that because we already knew that -2 was an intercept. And then we have the relative maximum where
The -1/2.
it's going from increasing to decreasing over -1/2. And then the y value, we don't know what it is, we have to find it. So So plugging in -1/2 to the original function, it's going to be -1/2 plus 2 squared over -1/2 squared minus 1. So that's let's see, -1/2 plus 2 is 3/2. And 3/2 squared is 9/4. Over -1/2 squared is 1/4. Plus 1, well, 1 is 4/4, so that's 5/4. And 9/4 over 5/4 is 9/5. Okay, so now we can do the first derivative graphing. I'm probably going to skip the second derivative stuff because it's a little bit ugly here. So let's start off with the intercepts. I've got a y-intercept of -4 and x-intercept of -2. Right, and I might want to give myself a little more room on the x-axis because I got a lot of stuff happening between -2 and 0. Make those x-intercepts a little bit. It's perfectly fine to make one axis not the same length or scale as the other axis. All right, so here are my x-intercept and y-intercept. And then I've got, let's see, vertical asymptotes at ±1, horizontal asymptote at 1. Use a different color for our asymptotes. So my vertical asymptote at ±1. Horizontal asymptote at +1. It's good to label your asymptotes. All right. And then we have all the first derivative stuff. So we know we have a relative minimum at -2 here. So that means this is going to be the bottom like this, right? It's a relative minimum. So the function's bigger on either side. And a relative maximum at -1/2 come 9/5. So here's -1/2. And 9/5 is almost 2. So we're kind of like right up here. So there's our relative maximum. And it looks like that, right? Relative maximum? Did I make a mistake somehow? That seems, so here's why I am concerned. So I was going to start graphing this. So let me start graphing it and maybe I'll figure out where my mistake is. But I definitely think I made a mistake somewhere. Yeah. Okay, I'm going to start graphing it and we'll figure it out. So I usually start with the y-intercept. And then I see that my function is decreasing. So right, I don't have the 0 here. My function is decreasing from 0 to 1. It's decreasing down like this. And then it's decreasing after 1 as well. So it's decreasing down like this. If you're decreasing on both sides of a vertical asymptote, from left to right, you're going down to -infinity, and then you're starting up at infinity, going down, 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 down. If you're increasing, you'd be going up and then up from -infinity. Now, the problem I'm seeing here is somehow this is supposed to connect to this, but I don't have any x-intercepts to pass through. Right? My x-intercepts were just -2, and that was it. I feel like I made a mistake somewhere, which is disappointing, but it's good to figure out where it is. So let's see. It's probably somewhere in the first derivative, not gonna lie. Let's check it out. So let's make sure I did this right. I did the bottom times the derivative of the top, and the derivative of the top is definitely 2 times x plus 2 to the first, yep. Minus the top times the derivative of the bottom, which is x plus 2 squared times 2x, all over the bottom squared. I factored out the 2 times x plus 2 from the top. So I was left with an x squared minus 1 and x plus 2 times x. And x plus 2 times x is definitely x squared plus 2x. And to minus all of that, so it's x squared minus 1 minus x squared plus 2x. The x squared minus the x squared cancel. The minus 1 minus the 2x is fine. And minus 2x minus 1 should give us x equal to -1/2. Okay, x equal to -2. Okay, plus or minus 1. Well, darn anyway. So if I plug in, Oh, I'm done. I found my mistake. So I was almost there. So the mistake is when I plugged in, so when I found the y value, I plugged in -1/2, and I got -1/2 plus 2 squared over -1/2 squared plus 1. Because it's actually over x squared minus 1. Okay, so that's the problem. So this should be a -1. -1/2 squared is 1/4 minus 1. So 1/4 minus 4/4 is -3/4. That's a totally different ballgame. The 4's cancel, you get 9 over -3, which is just -3. Sorry about that. So I shouldn't have this point right here. I should have this point right here at -1/2 -3, which makes way more sense. So that's a relative maximum. So what's happening is right here, you got a max, and then it goes down like that. And then on the other side of this, well, again, the function is decreasing here and then increasing upward. So check this out. It's going to be increasing, and I have to cross this horizontal asymptote. There's no other choice. If you're increasing like that towards the vertical asymptote, you have to shoot up to infinity, which means I'm crossing the horizontal asymptote right there. It's perfectly fine to cross the horizontal asymptote. It happens all the time. And then to the left, we're doing this. Now, I would say you shouldn't cross the horizontal asymptote unless you have to. And as you go out to infinity or negative infinity, you should be getting closer and closer to your horizontal asymptote value. So we just say, oh yeah, well, of course, as we go this way, it's going to get closer and closer to y. So that's what this graph would look like. And it does make sense that on this graph, you wouldn't say it's decreasing from -1/2 to infinity. You would say it's decreasing from -1/2 to 1, and then it's also decreasing from 1 to infinity. But it's definitely not decreasing from like here to there. It definitely gets bigger. So when it's undefined, we don't include the point in our interval of increasing or decreasing this. When it's defined, we do, right? Like f of x equal to x cubed, which looks like this. Even though there's a critical point at 0, it's increasing. We say it's increasing on the entire interval from -infinity to infinity because it's increasing, and it's defined at the point where the derivative is 0. Yeah, we definitely don't want to look at this. So we could look at the second derivative here. It's not particularly nice. What we would end up seeing with the second derivative is that it's concave down over here, somewhere here-ish, which means from concave down to concave up, and then it's concave down, and then it's concave up. One way you can tell by looking at a graph if it's concave down or concave up, I like to think about like a car driving along a road. Right, so if the car is turning, and we're like looking at it from the top down. So if the car is turning to the right, it's concave down. If the car is turning to the left, it's concave up. So here, the car, and we're driving right that way. So the car is driving. It's very slightly turning right, and then right about here, it starts turning left, turning way left. And then from down here, we're turning right, really turning right. But there's always that right turn. And then up here, we're also turning to the left, right? We're turning left, right? If we think about the car like that. So that's one way you can kind of think about the concavity. If you move from left to right along the function, if your car would be turning left, you're concave up. If your car would be turning right, you are concave down. I kind of meant to talk about other things today in addition to graphing, but look at us, we're just about out of time. So Friday, we will do more stuff. Let me know if there's specific things you want to see on Friday. I would imagine you guys would like to talk about optimization. That's probably the big thing that we haven't talked about yet, that you guys have talked about in class. But if you have other things you want to see on Friday, let me know ahead of time or let me know in class, and we will do whatever we need to do. Let me make sure everybody got the attendance form one last time. All right, there you go. Yeah, good talking to you guys. Thanks for talking. The few of you that did, I appreciate it. And I will see you all on Friday.